In Part 6 of Lecture 3, we will discuss process creation and execution. Before continuing with our discussion of the way in which the operating system manages processes, we need to distinguish between the mode of processor execution normally associated with the operating system and that normally associated with user programs. Most processors support at least two modes of execution. Certain instructions can only be executed in the more privileged mode. These would include reading or altering a control register, such as the program status word, primitive input-output instructions, and instructions that relate to memory management. In addition, certain regions of memory can only be accessed in the more privileged mode. The less privileged mode is often referred to as the user mode, because user programs typically would execute in this mode. The more privileged mode is referred to as the system mode, control mode, or kernel mode. This last term refers to the kernel of the operating system, which is that part of the operating system that encompasses the more important system's functions. The table you see on this slide covers functions that are typically handled by the kernel of an operating system. It could include process management functions, such as the creation or termination of processes, or their scheduling and dispatching. It covers process switching, process synchronization, and the management of the process control blocks themselves. It can handle memory management tasks such as the allocation of address space to processes, swapping, page and segment management. Similarly, can also handle functions of input-output management and support functions such as interrupt handling, accounting, and monitoring. Once the operating system decides, for whatever reason, to create a new process, it can proceed as follows. Assign a unique process identifier to the new process. At this time, a new entry is added to the primary process table, which contains one entry per process. Allocate space for the process. This includes all elements of the process image. Thus, the operating system must know how much space is needed for the private user address space for both programs and data, and also for the user stack. These values can be assigned by default based on the type of process, or they can be set based on user request at job creation time. If a process is spawned by another process, the parent process can pass the needed values to the operating system as part of the process creation request. If any existing address space is to be shared by the new process, the appropriate linkages must be set up. Finally, space for a process control block must be allocated. Initialize the process control block. The process identification portion contains the ID of this process, plus other appropriate identifiers, such as that of the parent process. The processor state information portion will typically be initialized with most entries 0, except for the program counter, which is set to the program entry point, and system stack pointers, which are set to define the process stack boundaries. The process control information portion is initialized based on standard default values, plus attributes that have been requested for this process. For example, the process state would typically be initialized to ready or ready suspend. The priority may be set by default to the lowest priority unless an explicit request is made for a higher priority. Initially, the process may own no resources, and by that we mean input-output devices and files, unless there is an explicit request for these or unless they are inherited from the parent. Set the appropriate linkages. For example, if the operating system maintains each scheduling queue as a linked list, then the new process must be put in the ready or ready suspend list. Create or expand other data structures. For example, the operating system may maintain an accounting file on each process to be used subsequently for billing and or performance assessment purposes. A process switch may occur any time that the operating system has gained control from the currently running process. The table that you see in the slide suggests the possible events that might give control to the operating system. First, let us consider system interrupts. Actually, we can distinguish, as many systems do, two kinds of system interrupts, one of which is simply referred to as an interrupt, and the other as a trap. The former is due to some sort of event that is external to and independent of the current running process, such as the completion of an input-output operation. The latter refers to an error or exception condition generated within the currently running process, such as illegal file access attempt. With an ordinary interrupt, control is first transferred to an interrupt handler, which does some basic housekeeping and then branches to an operating system routine that is concerned with the particular type of interrupt that has occurred. Examples include the following. A clock interrupt. The operating system determines whether the currently running process has been executing for the maximum allowable unit of time, referred to as a time slice. That is, a time slice is the maximum amount of time that a process can execute before being interrupted. If so, the process must be switched to a ready state and another process dispatched. An input-output interrupt. The operating system determines what I/O action has occurred. If the input-output action constitutes an event for which one or more processes are waiting, then the operating system moves all of the corresponding blocked processes to the ready state and blocked suspend processes to the ready suspend state. The operating system must then decide whether to resume execution of the process currently in the running state or to preempt that process for a higher priority ready process. Memory fault. The processor encounters a virtual memory address reference for a word that is not in main memory. The operating system must bring in the block, which is a page or a segment, of memory containing the reference from secondary memory to main memory. After the input-output request is issued to bring in the block of memory, the process with the memory fault is placed in a blocked state. The operating system then performs a process switch to resume execution of another process. After the desired block is brought into memory, that process is placed in the ready state. With a trap, the operating system determines if the error or exception condition is fatal. If so, then the currently running process is moved to the exit state, and a process switch occurs. If not, then the action of the operating system will depend on the nature of the error and the design of the operating system. It may attempt some recovery procedure or simply notify the user. It may do a process switch or resume the currently running process. In Lecture 1, we discussed the inclusion of an interrupt stage as part of the instruction cycle. Recall that in the interrupt stage, the processor checks to see if any interrupts are pending, indicated by the presence of an interrupt signal. If no interrupts are pending, the processor proceeds to the fetch stage and fetches the next instruction of the current program in the current process. If an interrupt is pending, the processor does the following. It sets the program counter to the starting address of an interrupt handler program. It switches from user mode to kernel mode, so that the interrupt processing code may include privileged instructions. The processor now proceeds to the fetch stage and fetches the first instruction of the interrupt handler program, which will service the interrupt. At this point, typically, the context of the process that has been interrupted is saved in that process control block of the interrupted program. One question that may occur to you is, what constitutes the context that is saved? The answer is that it must include any information that may be altered by the execution of the interrupt handler, and that will be needed to resume the program that was interrupted. Thus, the program of the process control block that was referred to as processor state information must be saved. This includes the program counter, other processor registers, and stack information. Does anything else need to be done? That depends on what happens next. The interrupt handler is typically a short program that performs a few basic tasks related to an interrupt. For example, it resets the flag or indicator that signals the presence of an interrupt. It may send an acknowledgement to the entity that issued the interrupt, such as an input-output module, and it may do some basic housekeeping related to the effects of the event that caused the interrupt. For example, if the interrupt relates to an input-output event, the interrupt handler will check for an error condition. If an error has occurred, the interrupt handler may send a signal to the process that originally requested the input-output operation. If the interrupt is by the clock, then the handler will hand control over to the dispatcher, which will want to pass control to another process because the time slice allotted to the currently running process has expired. What about the other information in the process control block? If this interrupt is to be followed by a switch to another process, then some work will need to be done. However, in most operating systems, the occurrence of an interrupt does not necessarily mean a process switch. It is possible that, after the interrupt handler is executed, the currently running process will resume execution. In that case, all that is necessary is to save the processor state information when the interrupt occurs, and restore that information when control is returned to the program that was running. Typically, the saving and restoring functions are performed in hardware. It is clear then that the mode switch is a concept distinct from that of the process switch. A mode switch may occur without changing the state of the process that is currently in the running state. In that case, the context saving and subsequent restoral involve little overhead. However, if the currently running process is to be moved to another state, such as ready or blocked, then the operating system must make substantial changes in its environment. The steps involved in a full process switch are as follows. Step 1. Save the context of the processor, including program counter and other registers. Step 2. Update the process control block of the process that is currently in the running state. This includes changing the state of the process to one of the other states, such as ready, blocked, ready suspend, or exit. Other relevant fields must also be updated, including the reason for leaving the running state and accounting information. Step 3. Move the process control block of this process to the appropriate queue, such as ready, blocked on event I, ready suspend. Step 4. Select another process for execution. This will be discussed later. Step 5. Update the process control block of the process selected. This includes changing the state of this process to running. Step 6. Update memory management data structures. This may require, depending on how address translation is managed. This may be required depending on how address translation is managed. This will be discussed later in the course. Step 7. Restore the context of the processor to that which existed at the time the selected process was last switched out of the running state, by loading in the previous values of the program counter and other registers. Thus, the process switch, which involves a state change, requires more effort than a mode switch. One traditional approach, common on many older operating systems, is to execute the kernel of the operating system outside of any process. With this approach, when the currently running process is interrupted or issues a supervisor call, the mode context of this process is saved, and control is passed to the kernel. The operating system has its own region of memory to use and its own system stack for controlling procedure calls and returns. The operating system can perform any desired functions and restore the context of the interrupted process, which causes execution to resume in the interrupted user process. Alternatively, the operating system can complete the function of saving the environment of the process and proceed to schedule and dispatch another process. Whether this happens depends on the reason for the interruption and the circumstances at the time. In any case, the key point here is that the concept of process is considered to apply only to user programs. The operating system code is executed as a separate entity that operates in privileged mode. An alternative that is common with operating systems on smaller computers such as PCs is to execute virtually all operating system software in the context of a user process. The view is that the operating system is primarily a collection of routines that the user calls to perform various functions, executed within the environment of the user's process. At any given point, the operating system is managing end process images. Each image includes not only the regions that we saw in an earlier slide, but also program, data, and stack areas for kernel programs. Another alternative, illustrated here on the bottom of the slide, is to implement the operating system as a collection of system processes. As in the other options, the software that is part of the kernel executes in a kernel mode. In this case, however, major kernel functions are organized as separate processes. Again, there may be a small amount of process switching code that is executed outside of any process. This approach has several advantages. It imposes a program design discipline that encourages the use of a modular operating system with minimal clean interfaces between the modules. In addition, some non-critical operating system functions are conveniently implemented as separate processes. For example, we mentioned earlier a monitor program that records the level of utilization of various resources, such as processor, memory, and the rate of progress of the user processes in the system. Because this program does not provide a particular service to any active process, it can only be invoked by the operating system. As a process, the function can run at an assigned priority level and be interleaved with other processes under dispatcher control. Finally, implementing the operating system as a set of processes is useful in a multiprocessor or multi-computer environment in which some of the operating system services can be shipped out to dedicated processors, improving performance. The slide suggests a typical process image structure for this strategy. A separate kernel stack is used to manage calls, returns, while the process is in kernel mode. Operating system code and data are in the shared address space and are shared by all user processes. When an interrupt, trap, or supervisor call occurs, the processor is placed in kernel mode and control is passed to the operating system. To pass control from a user program to the operating system, the context mode is saved and a mode switch takes place to an operating system routine. However, execution continues with the current user process. Thus, a process switch is not performed, just a mode switch within the same process. If the operating system, upon completion of its work, determines that the current process should continue to run, then a mode switch resumes the interrupted program within the current process. This is one of the key advantages of this approach. A user program has been interrupted to employ some operating system routine, and then resumed, and all of this has occurred without incurring the penalty of two process switches. If, however, it is determined that a process switch is to occur rather than returning to the previously executing program, then control is passed to a process switching routine. This routine may or may not execute in the current process, depending on system design. At some point, however, the current process has to be placed in a non-running state, and another process is designated as the running process. During this phase, it is logically most convenient to view execution as taking place outside of all processes. In a way, this view of the operating system is remarkable. Simply put, at certain points in time, a process will save its state information, choose another process to run from among those that are ready, and relinquish control to that process. The reason this is not an arbitrary and indeed chaotic situation is that during the critical time, the code that is executed in the user process is shared operating system code and not user code. Because of the concept of user mode and kernel mode, the user cannot tamper with or interrupt with the operating system routines, even though they are executing in the user's process environment. This further reminds us that there is a distinction between the concepts of process and program, and that the relationship between the two is not one-to-one. Within a process, both a user program and operating system programs may execute, and the operating system programs that execute in the various user processes are identical.